I mean,
Well,
what if I'm like staring at this thing and this big alien just pops up? I'd probably cry.
but speaking of jokes, or maybe not, but like in my other class, let's see, this is Thursday. I think it must have just been yesterday. I asked which planet is this, and somebody said, I don't know. So, I know. Oh.
Terrible.
Yeah,
Are they joking?
Yeah, I think so. I hope so. So, yeah, that's the Earth.
Mars.
No, Mars. No, that's the Earth. But in order to talk about the four rocky planets, the four terrestrial planets, Mercury, Venus, Earth, and Mars, we kind of start with what we know about Earth, and with regard to kind of what its layers on the inside are. So if you've ever seen the movie Tremors, now I don't know about Tremors 2, but the first Tremors doesn't start out where the scientist is basically taking seismology information. So basically she sticks a probe in the ground, and then she walks somewhere else, okay, and then she listens for waves, and then actually that's important because the little critters, you can actually, get the whole. But anyway, that seismology, that looking at waves that travel through the Earth's crust, that's how we understand kind of what we know about the inside of the Earth, okay, other than visiting dinosaurs and such like that. So we're going to look at the other planets in terms of the gray part is the core, the orange part is the mantle, and the tan part is the crust. Okay, so kind of from left to right, not in order how they are to the sun, but from left to right in order of size. Okay, so Earth is the biggest terrestrial planet, followed by its cousin Venus. Okay, and then we have Mars, and then we have Mercury. And now I know the moon is not a planet, but you can kind of see where it's terrestrial, and you can kind of see the relative amounts of everything. But check out the gray part of Mercury. Look how humongous its core is. Okay, I just think that's kind of an outlier, just interesting. So, kind of picking up where we left off a little bit with kind of the chapter before this one, when we talked about how planets came to be. We said that we'd use the word accretion to kind of describe how planetismals got bigger and bigger, and they kind of picked up matter that was in their kind of track. Okay, planets got bigger and bigger. And honestly, planets early on were very hot. And so just kind of like salad dressing, Italian salad dressing is a fluid, so also the planets were kind of ooey gooey. And just like with your Italian salad dressing, if you set it down, you let it kind of, the dense water settle out and the light oil float. So also, planetary differentiation is basically the heavy stuff, iron and such, sank to the middles and formed those gray cores. Okay, so honestly, if you're to drill down inside of any terrestrial planet, you're going to find iron in the middle. Planetary differentiation. Okay. So the gray is the core, the orange is the mantle, and the yellow, it kind of tannishes the crust. But there's one more important layer called the lithosphere. And the lithosphere, you can kind of see on here, actually takes the crust for sure, all of the crust, and the first part of the mantle. Okay, so one of the things about the mantle is the mantle has kind of a solid part, a rigid part that makes up the lithosphere. So this up here, that is the lithosphere. Okay, now when we talk about what's called tectonics, I learned that not just tectonics but plate tectonics. What we're going to see is it's the lithosphere, the crust in the top part of the mantle that kind of floats around in the liquid part of the mantle. Okay, tectonics. So one thing about rocks is we usually think of rocks as being rocks are rocks, right? The rocks today, they can't necessarily readily be deformed per se in their solid state. But even solid rocks can be, over time, deformed if the process is slow enough. So this analogy basically is if you were to take silly putty like she's taking it and kind of analogous to a rock, you can actually deform a rock. But if you were to take that same rock that you're trying to deform and to just not apply force over time, but apply force all at once, okay, that would be like what she did with her silly putty. Doesn't she look sad?
I'm like actually really glad that you put that up there because I was just about to tell you, the other day I had silly putty, like somebody like brought it into like my work and I had it and I was just like making circles, like just making the balls and I was like,
It's downright
and
therapeutic.
like, no, I was like, I can make the planet. So I like had them like by size.
That's adorable. See this
So
shirt.
I'm glad you put that up there.
This shirt, it's like the solar system, and it's got Pluto on there somewhere. Pluto's over here. It's like a family picture of
That's
Pluto.
so horrible.
I wore that tonight just for today. Oh, so the tectonic part, kind of the plates moving, the lithosphere moving, they move because of what's called actually convection. And 100 million years is a long time. Yeah. And I think we might have talked about convection before, but I'm going to kind of focus in on the core of the Earth there. And maybe obvious, maybe not, but the gray core, I'm going to say hot. Okay, very hot. Okay, and it gets cooler as you go from the core outward. So because it's hot, what happens then is it heats the liquid near it a lot. So that orange part is mantle, specifically liquid mantle. So you see when you know how hot air rises in our house? It's a similar thing about this hot liquid that's next to the core. Hot air rises because it expands and it's like, dude, I'm less dense than you, I'm going up. Okay, so this liquid mantle expands and it's like, hey, I'm less dense than the mantle around me, I'm going up. So the up legs shown here is there and here. Okay, so we kind of have two up legs. Okay, and then what's going to happen is it gets farther from the core, it gets farther from a heat source, and it will cool down. So it's getting cooler, 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 and then actually at some point it's going to start to fall again. Okay, cooler, 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 and it's going to start to fall again. Okay. And then it's going to sink down close enough to the core where it's going to heat up again, and it's going to go ahead and ride the wave up again, and then it's going to come back down again. It's very similar to a lava lamp, the same phenomenon. If you turn on the light bulb, it heats up the fluid around it, and so it expands and it rises, and then it gets cooler and it falls back down. Okay, so that's a convection cell. So convection, conduction, and radiation, these are all ways of transferring heat. Okay, so transferring heat from the inside of the Earth actually outward. And so like the title of this says, the Earth is actually getting cooler and cooler. It's cooling off just a little bit. So I talked about convection. The blobs, because this is hot, that sort of thing, okay? Now, conduction is sometimes what I call molecule to molecule. This has to happen molecule to molecule. A good example of conduction is like if you are heating a pan of water on the stove, and the handle of the pan is way far away from the stove. But eventually, especially if you don't have any insulation around the handle's going to get hot. And the handle gets hot molecule to molecule to molecule to molecule to molecule. So that is conduction. And so conduction shown here is just this little bit right here. That's conduction. Okay, basically the liquid mantle has stopped moving. Okay, it's ready to move back down, but basically that heat keeps moving out. The last one we've talked about. Okay. So one of the things I want you to kind of get a sense of is we can't visit these planets, but I want you to kind of picture what it'd be like if we did visit them. In fact, I didn't make it this semester, but one of these semesters I should say, describe your favorite planet, what it would be like to visit it, based upon what you know or what you found out in class. So if we were to step on Mercury, that's kind of what doesn't Mercury kind of look like the moon? And Venus, I know it looks kind of orangish, but the problem about Venus is it's really got a bunch of hazy clouds around it. Earth, Moon, Mars. So if I were to go back to that previous slide, do we have a slide? Okay. The previous slide that had the kind of pictures of the things you'd step on each planet. Mercury looks a lot like the moon. Mercury and the moon have a lot of craters, a lot of pockmarks. And what I'm hoping is that with chapter 7, you kind of remember what we talked about chapter 6. But remember I used the word chaos. Okay, chapter 6, our solar system wasn't as clean as it is now. Before things settled down, we had planets. We had a lot of crumblies running around, a lot of comets and asteroids, okay? A lot of impacts. So the thing about Mercury and the thing about the moon, do you guys buy this? They cooled off fast, okay, and they didn't have kind of that, the plate tectonics to kind of change their shape, okay, to resurface them in a way. So this is the Barringer crater in Arizona. Winslow. It's like the song, right? Okay. Now this is on Earth. This is on Earth, right? Yes, Arizona. I guess there's not Arizona on Mars or anything. So most of our craters are gone, but this one stuck around because it was more recent and very large. So this is one of the craters on the moon called Tycho, affectionately called Tycho Brahe, right? And there's many more craters still left on the moon than there is on Earth, and that's because of weathering and tectonics. So now, are you kind of good? We already talked about tectonics a little bit, but do you see where tectonics are like the lithosphere floating around on liquid mantle? Honestly, this idea of volcanoes kind of fits into tectonics as far as I can tell. Because that ooey gooiness coming out from the volcano, that's mantle, okay? That's liquid mantle. So when the volcanoes do their thing, basically they resurface, okay, the planet. So Earth has had its fair share of recent volcanism. Outgassing is basically when a planet burps, okay? Yep. And the Earth's, the gases we have in the Earth's atmosphere today were basically because the Earth burped them up. And the Earth's mass was sufficient to go ahead and have gravity to make them stick around. Okay, so tectonics, like I said, I learned it as plate tectonics, but it's the same thing. So can you see there the little convection cells, okay, down there in the liquid mantle? But didn't it say it takes 100 million years to complete one cycle? Isn't that like, oh my gosh. So we have a couple of options that can happen with these plates, these slabs of lithosphere that float around the liquid mantle. They can come together and create mountains, okay, or they can diverge and create trenches or holes or whatever you want to think, whatever you want to call them. So I think that's kind of cool. So do you see where up at the top there, where it counts, up at the top here, where basically you have two plates, okay, literally, and it's hard for you to see it, but this cell is going this way and this cell is going this way. So that makes this slab go this way and this slab go this way. And so they're converging and they create a mountain ridge.
So in that picture to the right, are they meaning that that land was one at one time and it got pushed apart?
Mm-hmm. Pulled apart, exactly. They're saying that the Red Sea is an example where plates were diverging. So here we have this plate going this way because of that cell, and we have this plate going this way because of this cell. So they're spreading apart here and creating a hole. And in the oceans, I know that we have you ever heard of like oceanic trenches? Like deep in the middle of the ocean where nobody is, there's these big crevasses. I know, it's called seafloor spreading.
that how islands were formed from volcanoes?
Some islands were formed from volcanoes. Yep, very good. And I think the Hawaiian Islands were formed from kind of like they're a chain that was formed as a plate moved over kind of a hot spot, where kind of just like the plate was moving and it kind of kept poking up. Cute little I almost said planets, cute little islands. If you go down, I think it must be actually more like, where's the Indian one? Right over here-ish, okay? But that was that place that had that bad tsunami around Christmas time. But I think it was over there. And the thing about tsunamis is tsunamis are directly related to what we're talking about. Tsunamis are basically where the plates have an ocean above them, okay, and so the plates jerk, and basically it's that jerk that creates a movement of water up and down, okay, which is okay if it's in the middle of the ocean, but that movement of water hits shore, and basically you have, piles of water on shore. So
Well, is that what causes earthquakes? They rub them together?
Earthquakes, yeah, there's a couple different possibilities, and a lot of them are just basically rubbing side to side. Yep, earthquakes, where the plate boundaries are. See, earth science would be another good class. So years ago, somebody looked at the maps of the continents, and they said, hey, this looks like a puzzle piece. And honestly, we can find features, for instance, that match up on these continents. Okay. And so we know that they used to be one big supercontinent. I learned it called Pangea. So I have a little video, I think, to show you. Oh yeah, no, that's not going to work. Gonna work? I think it's like 1 centimeter a year, I want to say. So it's not very much a year. But no. So tectonics have basically kind of erased what we used to be, we used to be, craters and all that. Tectonics has kind of resurfaced Earth's surface. Another thing that has changed what we used to be is water erosion. To me, though, this is the Grand Canyon. This has actually revealed more than it's really changed. Because the cool thing about the Grand Canyon is by basically eroding downward, okay, we basically can look back in time at what rocks were like. Oops, go back. Yeah, what I try to do is say this is the newest rock and that's the oldest rock. Okay. But so many planets don't have running water to erode them. The Earth has been through ice ages, just like the cartoon. Okay. So basically, where it's coldest at the upper latitudes, ice has come down, not to the equator, but pretty close almost to the equator, and then retreated. It came down, it retreated, it came down, it retreated. Okay, and in doing so, it kind of rubbed the Earth's surface too, and that's unique to our planet. Wind erosion has kind of done its fair share of erasing evidence of what we used to be. Okay, and this reminds me of kind of the flooding that we've gone through. Our 100-year floods that come like every 5 years. It can also resurface our surface. Okay. So one of the things that's unique to Earth, I guess relative to most notably maybe Mars and Mercury, is Earth has a great atmosphere. And here you see listed 4 things that the Earth's atmosphere gives us. Or does for us. Gives us or does for us. So,
I'm sorry, I missed that last one.
oh, okay. And I have a slide to kind of show you how, if we didn't have an atmosphere, our skies wouldn't be blue during the daytime. Now, at nighttime, of course, they're not blue. But if you were on the daytime on the moon, the skies wouldn't be blue. So this is kind of, I have this figure, and if you look ahead, you can see kind of the next figure where basically across the top you see different forms of electromagnetic radiation. Okay. So the longest one up here, although there is even longer than visible, of course we have infrared, microwaves, and radio waves. But the shortest one up here is the, we don't have gamma rays either. But the longer or the shorter the thing, it's blocked. Okay? The longer the thing, it gets through. That's kind of how you look at that. So this is a similar figure, but it has all of the forms of electromagnetic radiation that the Earth does for us. Blocks. Or allows. Okay. So the greenhouse effect, I have a little movie to show you, a little applet to show you. But just like, now I don't work in a greenhouse. I don't have a green thumb, so I kill plants. So I have not visited very many greenhouses or whatever. But what I do is, on a sunny day, and if I'm driving my car, and if my car is, got the windows up on a sunny day, when I come back in my car, it's really hot. It's the same thing. Basically, what happens to because your car makes your car hot, and when it's sunny, is that sunlight has gone through your windows, okay? And if you have a dark upholstery at all, or even if you have a light upholstery, basically that sunlight has interacted with the matter in your car and is turned into thermal energy. Now, thermal energy here is shown in little red, okay? So basically, picture the thermal energy of your car trying to get out. So here's the deal. It's going to try to get out. The heat's going to try to get out. But honestly, that glass, even though it lets light in, it's a pretty good insulator as far as thermal energy goes. So it lets the light in. Okay, your light turns to heat, basically, and your heat tries to get back out again. Okay, so that's what happens in our cars, and that's what happens in greenhouses. They just have a lot of glass. Okay. And the thing that makes it with regard to planets is those little dots, those are gases in the planet's atmosphere. So our planet has, some of its gases are good at blocking heat. Okay, that makes it a greenhouse gas. So this little applet I'm going to show you, it's kind of cute. Okay, so you see the yellow is the sun coming in. Okay, the sun interacts with the planet, okay, and then that planet will react from that sunlight by turning some of that sunlight into heat, and then you see the planet trying to cool off. But in this case, there's no atmosphere, okay, so the planet's heat that it got from turning sunlight into heat, it's gone. So if we click on this, add an atmosphere. Okay. So now those particles you see are the atmosphere of this planet. Okay. And those particles are good at, they are greenhouse particles. And what greenhouse particles or greenhouse gases are good at is basically absorbing heat that the planet leaves or redirecting the heat. And that's, the heat is the red. Okay. So notice some of the heat gets out, but some of it is kind of redirected back down to the Earth, or it's just kind of absorbed. It makes the atmosphere warm. Okay, so that's greenhouse effect. I thought they did a good job there. So greenhouse gases, I've got a few listed there. Oops, sorry. So, of course, carbon dioxide, CO2 is in the news. Carbon dioxide, CO2 is what you get when you burn fossil fuels. It's unavoidable. It's efficient burning fossil fuels. But water, I'm going to put a little G next to that H2O. Okay, so water in its gaseous state, water gas, is also, water vapor is also a greenhouse gas. Put vapor, okay? And the CH4 is methane, okay? Okay, so this is funny. It's been a few years ago, but did you hear about the cow tax? Congress, or somebody in Congress. Cows have several stomachs. And I think related to their several stomachs, they put out their fair share of methane. Okay? And so methane is one of the gas molecules in our atmosphere. It's got a warming effect. So then the thought is to tax those farmers with those cows putting out that methane. I don't think they did. I just think that's funny. Okay. So greenhouse gases, what are they? They're anything that absorbs infrared radiation. Next to infrared radiation, I'm going to put heat, just so we're all kind of on the same page with that. Some of infrared radiation is heat. But the thing I think is striking is the fact that just regular old nitrogen and oxygen, like 78% of the gas in this room is nitrogen, and about 20% is oxygen. So they are also greenhouse gases. Takes us for a toasty. So just one more kind of thought about that. We're going to talk about Venus here after break. And Venus, remember I told you that you really can't see Venus? It's because it's got these clouds. Maybe I didn't say that, but you can't. Okay, it's very cloudy. Okay. And those clouds are great, thick molecules that are greenhouse gases. Okay, so actually it has, and it can have what we call a positive feedback mechanism, in that if you have greenhouse gases, they can kind of ramp up, kind of have an out of control heat effect, greenhouse effect. So a little is good, a lot is bad. Okay, so one last thing about the Earth's atmosphere. So this is kind of a busy slide, okay, but I guess in this class, if you could just know that our sky is blue because of Earth's atmosphere, I would be happy. And then related to that, if you want to let your mind wander and say, well, the moon doesn't have much of an atmosphere, so if I were standing on the moon in the daytime, the skies would be blank in the daytime. I just think that is so cool. So I need to draw your attention to, this is actually coming from the sun. The sun is sending all colors of light. And I know there's just the red and the blue represented here. Roy G. Biv. The sun is sending all of that. So out of all of that comes from the sun, what happens is that the blue, actually the blue and indigo and violet, are scattered. Okay, and can you see the scattering here? Okay, the blue component of light coming from the sun is kicked around. And it's that kicking around, it's that scattering that makes our skies blue. So now the way you read this is you are looking down at the North Pole. I'll put NP for North Pole here. Okay, so let's see this, it's going counterclockwise, right? So actually we're at dusk, does that seem right? Noon in Hawaii, okay, yeah, no, we're at dawn. Let's see, counterclockwise, I was going clockwise. No, we're at dawn, I take that back. All right. So at dawn then, it says sunset. Well, anyway, the sun's up there and the sun is low on the horizon to the person in Florida. So now the thing that gives us our reddish sunrises and sunsets when the sun is low on the horizon is the fact that we have scattering here, scattering here. Basically, when the sun is low on the horizon, the atmosphere is thicker, okay, that the sun has to go through. So we have more scattering of blue, actually blue, indigo, violet, and it leaves those longer wavelengths, the red, orange, and yellow, to make it through. That's why our sunrises and sunsets are minus blue. They're just beautiful. One more, Waldo?
Yes.
So let's take a break, 10 minutes-ish. That puts us about 7:35, 6:35, excuse me.
7:35 sounds good to me.